Hi, Michael. Are you watching? If so, what I need is your Gmail account or other Google account. I will watch for it in my Gmail or other. Let's see. looks like the message you sent to me was from a Hotmail account. And so unless you've created a Google account using your Hotmail address, I don't think that'll work. Okay, I got a couple people watching here, so I've just attempted to send invites via the Google Hangout interface, and we'll see if this works. It is always a new wrinkle with Google Hangouts, and once it's running, it's fine, but getting people into it, it's just always a serious pain. Okay, let's see what we can do here. It didn't like that. Let's try again here. Okay, Mike, you should have an invite there, so you can actually join here, either in Google Plus or in Gmail or somewhere, wherever they're choosing to stick it right now. Okay, Vic, let's see if we can get you in here.
Can you hear?
I just heard something. This looks like Mike. Yeah. Okay. Oops, and you just dropped out. Okay, I may be having a slight problem with my network here. Let's see. Okay, Michael, can you hear me? Okay. And Michael, your image is frozen here. And it's not liking adding Vic, so let's try this once more with feeling. It is not liking inviting Vic here, and Michael, you are showing up as in the session, but now you're dropped. Now you've just dropped out, so I'm not sure what is going on with that. Okay, Vic, can you hear me? Let's see here. Yes, Michael, if you let's see if that if moving to another location helps your connection there. Okay, Vic, I assume you're looking at it on the Google Plus event page. Can you just type something in the window to let me know that you can hear me? Aha. Okay, so I think I have finally found this elusive link that will let somebody join. So Vic, I'm going to try mailing this to you here. Oh man, it's always something. Okay, why can I not? Why is this not letting me? Okay, so a few wonderful technical issues to get this kicked off for tonight here, and it's possible, but this has hung on me, so let me see. Yeah. Okay, for some reason it looks like Chromium is hanging on me here. I might have to stop this and let's see. Okay, Vic, I just tried sending it to you via email here, so give that a try and see if you can make it in. Okay, so Vic, if you try clicking that link here, hopefully we will make it through this. Oh, that sounds promising.
Hello.
Hey, Vic.
Hi, how are you?
Doing all right. How are you doing?
Oh, good.
Excellent.
The UI is so confusing.
Oh, it's terrible. Okay, but I think I have finally figured out how to get the invite link. Because if you go to invite someone, it wasn't letting me send an invite to you, but it actually showed the invitation link there, even though it's available nowhere else. So, okay, so I just posted that on the event page, so hopefully anyone else who comes along can use that to join. Michael said that he was going to try to find a better reception for his laptop here.
Okay.
So I guess we just chill out for a few more minutes.
Yeah, I'm just I read through the chapter a while ago. I'm just kind of skimming.
Yeah.
Refresh my memory.
Right. Maybe I'll find a link to. I don't have all of the exercises written up, but I've got a bunch of them. So let's see. Michael, is that you?
Yeah, hi.
Hi. Okay, great. Okay, and we've got Vic, and I'm just going to check the RSVPs here. We had one more person. Daniel posted saying that he wasn't going to be able to make it. And Michael Reichner had RSVP'd, and I sent him the actual invite, so hopefully he'll be joining if he comes along. Okay, let me find the write-up for my exercises here. Hold on just a minute. There we go.
It could be feedback.
Oh, hey, Michael, you made it in too. Great. Though you're muted if you're talking. And it looks like I am hung again. Wunderbar.
So, Paul, this is Michael. Which exercise set are you talking about?
So this discussion for tonight is on section 2.1.
Okay.
So yeah, so we've sort of been going through this at a sort of irregular pace here. Have you looked at much of the book yet? Have you? I think you mentioned
Well,
in your.
I
Go
only
ahead.
downloaded it maybe an hour ago, and started reading chapter 1, which I found very interesting. I'm just kind of breezing through what the beginning of chapter 2 is about. So just bear with me while I catch
Sure.
up to you guys.
Sure. That's okay here. And once again, my actual Hangout windows have completely frozen here. So I'm not getting any video updates at the moment.
Okay, well, I don't think I'm necessarily going to contribute a lot, but I'll certainly benefit by listening. I think we lost Paul.
Boy, I have
Hey.
to say that Google is becoming less and less usable as time goes on. And Michael, you are muted, you know. Not Michael in the car, Michael Reichner.
Yeah, I had some problems getting in originally.
Yeah, technical problems seem to be the order of the day here. You'd think that since this is, what, the fourth session, we'd have it worked out by now, but I guess that's the way it goes. So, okay. Oh, so I'm going to, instead of trying cutting and pasting, since that seems to crash the app here, I am going to... Okay, I just posted that URL to the other page there. I'm not sure if that shows up in this chat or not. Oh, this is so terrible. Excuse me. I sincerely hope this does not cause it to crash. There we go. So hopefully that link should then HTML version of my version of the exercises. Well, putting that aside for the moment, so I guess where is everyone at with respect to the to sort of working your way through the chapters here. Has everybody? I know you haven't, Michael, but is everybody else up to 2? Vic, I think you said you were looking at 2, but you hadn't had a chance to do any of the exercises. And Vic, you're muted.
That's about where I am. I've read it, but I haven't done any of the exercises.
Okay, that's cool. And Vic, you are muted.
Sorry. Yeah, I've read it, but I haven't done the exercises.
Gotcha.
I'm just looking at the church numeral stuff right now, which is kind of improving.
Gotcha. Okay, so just sort of my thoughts on section 2. So there's not really a lot of sort of new serious meat in chapter 2.1 compared to section 1.3. So sections 1.2 and 1.3 sort of dumped in a lot of the functional stuff. And if you hadn't previously worked with functional programming concepts, I suspect those may be sort of a bit of a challenge. But if you've done something with, a Lisp or even, more functional bits of Python or Ruby, there's not a lot of super challenging stuff in there. And I think the main point of 2.1 is to start trying to put those ideas to use. So, finally we get the list introduced and cons. So this is the first point we have actual data structures that we're working with. And so of the exercises, just let me share my screen here. No, infinity. Okay, let's see here. Okay, can everyone see my screen okay?
Yeah, I can.
Okay, great. Okay, so there's not a huge number of exercises here. You can see I did a bunch of them. I did not actually complete all of the last few. So section 2.1, the exercises, most of them form sort of an extended example. So it's the process of so in sections 1.2 and 1.3, they do a lot of repeated exercises where they present the same type of problem in related ways to try to get you to just keep bashing your head against them until you start thinking that way, like the converting between the recursive process and the iterative process. And we can certainly dive into that, Michael, if you want to just sort of catch up and do some general discussion on SICP. But what we have here then is, and so that is most of the exercises for 2.1.4. Exercise 2.1 is a pretty straightforward one. And it's really just a minor extension to the version of make rational that's presented in the text. So the key there is that normalization. So in what form do people have the book? Do you have the PDF version? Are you reading it in Emacs? Do you have a physical copy?
I personally am reading PDF.
Okay.
I've got a website I've been using. I'll post the link in there. It has a fairly nicely formatted HTML version.
Okay, cool.
I've got hard copy and PDF.
Okay, cool. So let's see here. I'm just flipping through. So I guess this is a pretty small group here. How do you guys want to handle the discussion tonight? So in previous versions we'd been talking about discussing different takes on the exercises. Obviously, since most of us have not worked through those. That's probably not the best approach for tonight. So what would you guys find useful for this discussion tonight?
I would be interested in talking about the exercise 2.6 right now, the church numerals.
Oh, yeah. Okay, well, that's I think that's one of the two most interesting exercises for sure. It's 2.6. Yes, so this one is definitely one of sort of the key insights of the chapter. It doesn't really tie into anything else that's presented except sort of this concept of, the mathematics that underlie functional programming in general and sort of the inspiration that drove Lisp from the beginning. So if you actually tackle this exercise, it's really a process of substitution, and it's a process of more or less figuring out what name means what in what context. Let's see here. Okay, so let's look at my write-up for this one here. This might be the best way to do it here. Okay, can people read my screen share okay there?
Yeah.
Okay, is that font size okay and everything?
Mm-hmm.
Okay, excellent. Okay, so so here's the two bases of this discussion here. So you've got 0, and you can see that 0 is defined as, so does everybody have a clear grasp of the concept of a lambda? Michael,
Mm-hmm.
I think you said that you hadn't looked at SICP and you hadn't used Clojure much before this. I guess we've got two Michaels.
No, but I've used Haskell some, and I've used F#.
Okay, so no mysteries here.
Yeah, no mysteries.
Okay, excellent. Right. So what we have here with 0 is it is a lambda that returns another lambda. And the lambda that the inner one returns is going to basically be this value. It's more or less an identity function. It's just going to return whatever is passed to it. So let's see here. Okay.
Okay. It's pretty straightforward.
If I'm understanding that correct, it says 0 is itself becomes a function that takes an argument and ignores the argument it takes and then returns an identity function?
Yes, exactly. And I have messed up a couple of my settings here. I'm not sure why this is not here. Okay, so 0, however, does take an argument, and you can see that argument is f. So more or less, 0 is going to take an argument f, which it ignores, and it's going to return another lambda that is the identity function. So if we say 0 foo or whatever, 0, it's going to return a procedure. And if we evaluate that procedure, so we stick an evaluation position there, and that's going to return B. Because this returns your anonymous function that takes a single argument and returns that argument. But 0 itself throws away its argument. So what 0 is doing here is it's setting up a base case for us.
Mm-hmm.
And now this key one here is add 1. And so this gets a little hairy, as you can see. So add 1 is named. Let's see, and I think oh yeah, so I wrote this one a little bit because I found the way it was done in the text a little confusing. So, so what we have here is add 1 returns a lambda that returns a lambda that returns a, is a lambda, excuse me, that returns a lambda that returns a lambda. And you can see that starts to get a little hairy. So the key there is to really just start substituting. So in sections 1, 2, particularly of the book, there's a lot of time spent on the substitution process, and working through this one, that's really all that's required. So we start off add 1, 0. So we start off, we can substitute in the 0 in the middle here, which you can see is just that same 0 we were looking at before. And then we have to wrap it with add 1. And so then we just replace add 1. In this case, the n there, this is going to be the n in the context of add 1. So that's going to be substituted here, and so on. And so if you look at how this is structured here, this here is the add 1 itself, and then this is what's getting passed to it, which is 0, which is the argument to add 1. Okay, is that clear?
Sort of.
Yeah, it's a little...
I see what you're doing. I don't know if clear is the word.
Yes, that's a fair assessment. Okay. Yeah, I mean, what I found trickiest with this one is keeping all the names and numbers straight.
Right.
So, for example, one of the challenges here is that, so you notice that I changed this 0 to x's instead of n's, because the n's are confusing in this context.
Right.
So that way you can keep the x separate from that n. Because the way that schemes bindings are set up, it's lexical bindings. So that means it's going to use the value of n it finds in the nearest enclosing scope. So really, all this line 3 is here is this is the substitution for the body of add 1. And this is the substitution for 0.
Okay. And then so any other number can be built by just repeatedly adding 1?
That's the theory, yes. So the first step of this exercise then is to come up with an explicit representation of 1 in this notation. And so to do that, we apply add 1 to 0, and then we're basically going to be simplifying it by going through just the normal substitution steps to see what comes out. So, okay, here we go. So here is the next step. And so, okay, so the thing to note there is since this is in the execution position, this gets substituted for the n here. And then that means it also is going to be substituted here. So this portion here goes to there, which, as you can see, ends up being here in the substituted version. So you might have to stare at this a little bit to see the equivalence. Yeah, so Michael, if you haven't looked at the text before, this is kind of deep waters to be jumping into at the start.
Well, I mean, I've read about church numerals, so I understand what's going on.
Oh, okay. Cool.
My main challenge is that I was trying to do this from my iPad, and it looks to me like the leftmost 3 or 4 characters of your screen are being chopped off.
Oh, okay. Let's see here.
So that I'm having.
Yep. Okay.
I mean, I can. But I don't want to drag you down into my little technical.
No, that's fine.
What I'm trying to do is
How's that? Is that any better?
Oh, I think it is. Well, no, I'm still losing. You know, I think it's my thing, really, to be honest with you.
Okay, I can.
I'm still
position that.
losing the first couple of characters.
How about
Oh.
now?
Yeah, that's better.
Okay.
Yeah, that's better.
Okay, good. Yeah, just kind of a cheap splitting of my screen there. Okay.
Okay, so while you guys talk, I'll just look at this exercise and see if I can make sense of it.
Yeah. So, and so really the main thing is just keeping straight what goes where. So this substitutes for the n, and then as it gets called, the body of the lambda just gets substituted out to become this lambda, because that is what's returned by the outer lambda. This outer lambda, when it's called, since it's in the call position there, is going to return just its body there. And with this substituted in for n. So that's what we see here. And so there is our base value of 0 substituted in for the n.
Mm-hmm.
Okay, so our next simplification step is pretty straightforward. And in that case, we have this lambda here, which, as we can see, is also in an execution position. And so it's got the f there. It's going to be applied. And so, more or less, this is... So more or less, we apply this, and we end up stripping out one layer of the lambdas as it gets applied. And since this is our 0, this f is basically ignored. So that f is just completely thrown away. This inner f, that is, not the outer f. Because as we said, so this is a lambda, this is our 0, as we saw in the REPL. You know, it's just going to return lambda x returns x. And so that's what we've got here. Lambda x returns x. And we just repeat that substitution process again. And that gives us, so that should be a 6 there. It's very simple. F comes to x. And I think I might have messed up that parenthesis there because this should be applied to this x. And so then that is basically, this here is just the identity function. And these inner x's are different from the outer x. But it just passes through for purposes of this. And we replace this entire sub-expression here with just x. And then we have f of x. And now, the key here is that this is what we end up with. Whoa. Oh, okay, so Michael Claggett just had to drop out here because he had to go pick up his wife. So, okay. Okay, so the final end game here. Okay, thanks for joining us, Michael. Yeah, hopefully you'll be able to make some more in the future here. Okay, and so what that leaves us here at the end of the process is a function. So that takes one argument, and okay, so yes, so define one. So this, another way to write this is actually, of course, I'm forgetting my scheme syntax here. F. Okay, those are equivalent there. So once we've substituted this all the way through, what we see then here is we get something that applies, it's a lambda that applies a function f once. And so, in fact, calling this 1 is not the best way. It's almost be better to call it once. But this is so how the church numerals are actually defined. So, okay, so how does that look to people? Michael, Vic?
Yeah, I just need a second to read that. Okay.
This one is not straightforward to just kind of grok.
Right.
So there's a really good Wikipedia page on church numerals, which sort of goes through like all the different things you can do with them.
Yeah,
And
I've seen that before. I think I need to like sit down with a pencil and paper and like really work through it to get it.
yeah, that's really the key to this one. It's just making sure that you're substituting the right F and the right X in the right context. And I found that since all of these functions are using the same F's and X's, it's a little hard to keep them straight sometimes. But really, what we end up with at the end here is then this add 1 to 1.
Right.
We substitute it through, and we end with, we won't step through all of those specifically, but anyway, what we end with is a lambda that returns a lambda. And what it does is it applies its function argument twice.
Okay.
And so that's sort of the fundamental realization that sits at the basis of church numerals. And so then the final step here is using this type of notation to add two numbers together. And is that part of the exercise? I think it is. I'm trying to remember here. Just flipping back to the text here. Yeah, directed definition of the addition procedure. Oh, and it's very straightforward. So, okay, so the key here when you're coming up with addition is you have two functions that are specified in this notation. So you've got your function p, which is going to apply something, x times, and you've got your function q, which is going to apply something y times, say. So in this case, we can just call one with the other as the argument, and it's going to then do x times plus y times just sort of for free. And the final lambda that's returned has this argument x at the end, and that's like our base case. So that if it's did I have an example of that? No, I didn't have an example of that. But so in this case, let's see here. No. Okay. Anybody know off their hand how to do concatenation in Scheme? Okay, I'm just going to check this fast here. Well, we can actually do it like this. In fact, let's try this then instead. So 0, we'll just use plus. actually use the numeral 0 as our base case. And so now, if we add 1, so what this gives us, this is a procedure. Okay. Okay, so as you can see, actually putting this into practice is a pain. I should have worked this one out in advance. But the general idea here is if you use the 0 as your base case and then plus, there's the problem. Let's see. I almost got this here. That is not quite right. No. Okay. Well, I don't know. Do you want me to try to sort this out? What are you guys thinking about this here?
I think it's okay. I get the idea here.
Okay, cool.
And unless you wanted to see it, Michael. I see you got your color scheme sorted out, too.
Well, I kind of got my color scheme sorted out. I took a cheap way around. So I've still got the problem, but I added a hook so that every time I open a new frame, it resets the two colors that are a problem.
Okay.
So basically it sets the colors wrong and then it sets them right. So the problem is still lurking there under the surface, annoying me. But okay. at least it's a quick fix.
Right.
Okay, so
I've actually got a question.
Yeah.
We'll start with the easy one. 0. Why does it require nested lambdas?
Okay, so part of the definition of lambdas is that they just take a single argument.
Ah, gotcha.
So if you've done any Haskell, you may notice that every function actually only takes one argument.
That's called function curry, right?
Well, so if you're currying a function in Haskell, it's similar to partial application, but it's a little different because you actually, apply the certain arguments to the function, and so you have it pre-calculated to that extent. And the difference to a language like Clojure, where you actually have multiple argument functions, is that in that case, more or less, it just saves all of the values for the argument and then calculates them all at once. So when you're looking at a Haskell function type, it's going to be something like, I forget exactly what the syntax is, but it's going to be something like, so that's how you do a two-argument function. This is a function. Um, yeah, so this is just a single function that takes one argument of type A and returns another argument of type A. And so then to add the second one, it's actually going to return a function that's going to expect another A, and then you finally return it. So when you're querying, basically what you do is you fill this in with an actual value. So that's part of the reason this notation is so messy here then.
Right.
So, okay.
Thank you.
Sure. That was question 0. Question 1?
Well, I mean, the same issue applies to add 1, but I mean, now that I understand why.
Oh, I see. Gotcha. Yeah.
I figured it out myself on 1.
Okay, cool. Okay. Yeah, this is fun stuff. This is one of those that's, I think, kind of interesting for sort of the broader insights it gives you about the underpinnings of functional programming, but it's not really something that you're going to be using every day. I mean, it's not necessarily going to change the way you write code a lot. It might help you a little more if you're doing something in Haskell, but this is a very inefficient way to encode your numbers. Yeah. So it's interesting more from a theoretical. Beg pardon?
You mean chart numerals are very inefficient?
Yes. Yeah, they're more of a theoretical construct than an actual practical way you're going to be writing code for the most part.
Yeah, we did chart numerals in functional fall.
Oh, did you? Awesome.
Yeah.
Okay. Did you take a look at section 2.5 at all? Or actually, problem 2.5, exercise 2.5.
Exercise 2.5.
So that is the. So I think that particularly 2.5 and 2.6 are the most interesting exercises in the chapter. And 2.5 is slightly more practical. So it's not something you'd actually do for the most part, but once again, it's a way of, I think the useful thing here is looking at how you can do something creative within the constraints you have. In this case, to store 2 numbers as a single number. So in this case, we're exploiting a bit of number theory here, just to say that okay, so we can if we have a number A and a number B, if we multiply 2 times A and 3 times B, and then multiply the 2 together, if you think about how that factors down at the bottom level, that'll be 2 times 2 times 2 times 2 A times, and then B times B times 3 times 3 times 3 B times. And so it's a pretty straightforward implementation for this. And for this, you want your exponent function, which is pretty straightforward. We got that from the previous chapter. And all you need to do then is you need this function here, factor count. And all it's going to do is count the number of times that a particular number is a factor. That is to say, the number of times you can divide the base number evenly by that number. And so it's very straightforward then to fetch the numbers out. So if you have a number P, you just count the number of times 2 goes in, and that gives you your A. But the same thing for your B.
Okay, so how do you get from that to representing any number as 2 to the A, X, 3 to the B?
So that's what this first one does here. So the exponent function, it basically, so if we have 2 times 5, it's going to basically give us, right? And if we've got exponent 3, say, that will give us 3 times 3 times 3.
Right.
And we multiply those together. And so what this comes up with then is a single number, 2, 4, 8, 16, 32 times 9. Okay.
Right.
So anyway, so that gives us our number. And so this is sort of our faking out the cons here. And so we come up with a single number that ends up being, I'll change this to something easier.
Yeah,
So
no,
4
I
times
think
9 equals 36. So if we want
I misunderstood. I misunderstood. No, I think I misunderstood the problem. I mean, given that, let's say 17 is 2 to the 4th plus 3 to the 0, I thought the problem was that it was asking you to determine what A and B were from the number 17.
Okay, so it's actually a two-way problem. So it isn't but it's not a plus. It's actually a multiplication. Because each of these are prime factors, and if you multiply the prime factors, you're always going to have the same number. So we stick in 2 2s and 3 3s. The only way we can factor this number is as 2 times 2 times 3 times 3 times. If we break them down to prime factors. And so that's what this step does here. So icar, so let's say that we did a cons here. Cons, so we, right? And so what this would end up giving us is 2.3, right? And so if we wanted the first one, we'd just do car 3, and that gives us 2.
Right.
What we're doing here is a sneaky version of cons, which we're calling icons. And so icon that we end up with 36. So the question then that the problem goes on to ask is, how do we get this out? So what's the equivalent, this what I'm calling here, of icon?
Okay.
And so that's what we have the implementation of right here. So we reduce that to factor of 36 and 2. And so what factor count does is it just goes through and checks to see how many times we can evenly divide by the factor, which is in this case the factor f, which is 2. And that's just a very straightforward stepping through it repeatedly until the remainder is not 0. And so what we get out then is 2, because we can only divide it by 2 times before we start getting our prime factors of 3. And similarly, the I cut 2, 3, 36 and 3 gets our 3 count.
Could this be done with any prime bases, or just 2 and 3?
Nope, any prime bases.
Okay.
So if you added in 5s, you could then encode 3 separate numbers.
Okay.
So I thought this one was a lot of fun, actually. And you probably aren't going to be doing a lot of that. You get into some similar things when you're doing like a lot of bit level operations. Sneaky ways to encode 2 separate numbers, using XOR and so on. But I guess the key insight for me here is, it sort of doesn't matter how your data is encoded behind the scenes, as long as you've got functions to stick it in and put it out. So take it out again. So it doesn't matter if you're using iCar or car, and if you've got a cons cell on the back end or this combination of prime factors. So taking that a step further, you could then start. So what they're working towards here is the idea of abstraction. So if you have something like a closure protocol, or some sort of polymorphism, where you've got the same function, and then you've got some dispatcher which is going to say, okay, I have this kind of object behind the scenes. Then it doesn't. Then the user doesn't have to care which representation is behind the scenes. At this point, they aren't really saying that super explicitly, but that's, I think, what they're starting to work toward. So one more there. 2.4 was sort of along the same lines. And so this is using lambdas as, let's see here. Okay, I haven't looked at this one in a while. Okay, right. Okay, so this one is, again, a little tricky. So we're defining a function cons here, a completely separate cons from the normal one, that accepts two arguments, x and y. And it is going to return an anonymous function that applies another function m to x and y. Okay? So you've got sort of this this potential hanging out here. So you've got an anonymous function, and it is waiting for a function. And as soon as it gets that function, it is going to apply it to x and y. And so that's what car of z does here. So what it does is it takes a function as an argument. Okay? And it's going to take that function. It's going to pass this anonymous function as the first argument. And return the value of that application. So can you see how that's going to work in this context here? Okay, let's see if I did a substitution here. That might make this a little clearer. Okay, so here we have cons of x and y. Okay, so the cons of x and y is, as we defined it above, it returns this anonymous function that's going to wait for a function m, and it's going to apply m to the two arguments that it closed over. Okay, so now we substitute in car itself. And car, there we go. So car of z, it's going to take its function, or its argument, and apply it to this as the first argument. Got it?
Yeah.
Okay. So when we do that substitution there, this is the first argument, right? So this is our z in this case. So that gets substituted in here. So this gets substituted here, which you note is a valuation position, right? And so it's going to get one argument, and that argument is this lambda. Okay? So this lambda is being called with this lambda as its argument. Okay? So this is going to get substituted in for the m. Make sense? And then that m gets plopped right here, right?
Yeah.
And so that gives us this. So we stick this in the M, it passes through to here, and so that returns this with this in the M position, and that's what this is right here. So there's that, and here is our X and Y. And so you can see it's going to evaluate this anonymous function with X and Y in place of P and Q. And that's what this is here. So it substitutes those in, and it's always going to return X, the first of those arguments. And that's an evaluation position. So it evaluates it, out pops the X. Okay, what do you think? Follow that? So I'd say this is another one that it's worthwhile to try to just walk through, just write it down on paper. Doing it on the computer is probably more trouble than just trying to write this out by hand.
Yeah, that one, and it makes sense now that I see it. I think sometimes for a book like this, maybe less and more descriptive names would sometimes help.
Yeah, I agree. And I mean, this is one of the places where all the parentheses do make it a little hard to sort of tease out exactly what's going on. So, and so things like this, where you have, this lambda, working out that this is actually the argument to the lambda at this level is, it just takes a lot of focus.
Right.
And I have anything else, that's all I had for that. So
that lambda PQ that returns P, is that the K combinator there? That's
so actually, I don't know the K combinator. So what is the K combinator?
I think it's a function that takes two arguments and returns the first argument.
Oh, yes, that's exactly a K combinator. You're quite right.
I'm not 100% sure.
No, yeah, I just did that is correct. Right. So that is what car is defined as almost. So car is rather applying takes a function and gives it the K combinator, which will then spit back out. So, and then the function that's supplied takes that and then applies that to the two values that it closed over when it was created, which is when the cons was called. So the cons latched onto those original X and Y values. And it's just waiting for the function to be passed to it, which is going to say, okay, fetch out X or fetch out Y. And that's what this is here. So this is saying, fetch out the one in the X position.
Okay. And so cdr is defined in the same way through returns Q, I assume.
Yes, exactly so. Exactly so. So this one, I think, is, I don't know, from my opinion, this one might be the most important exercise in the chapter, because the other two are kind of neat tricks, but this one, this is the one that I think actually does the best job of getting you to think functionally. That is to say that how functions close over their, or how lambdas close over their data, and how you can pass functions to other functions to perform operations. So this is a pretty abstract implementation, but I mean, if you've done any functional programming, I'm sure you've seen this kind of doing work by passing other functions around. So there's a lot of different things you can kind of slot into variants of this pattern.
Right. Yeah, okay. The takeaway is that you could essentially build any data structure you wanted just by building up with closures.
Yes, yeah, that's another So sort of exactly how flexible lambdas are is definitely, sort of the other key point to take there. And I'm not sure if we ever do a version of these for list. Well, actually, this means that we could, in fact, use this to build lists, as long as we had some sort of a nil value. So in scheme/lisp, your list is conventionally, a series of cons cells, right. And the left cons cell, the car of the cons cell is the data, and the right of the cons cell is the next cons cell, all the way down to the end, until you've got a nil, which in Lisp is the same as the empty list, in the final cutter of the last cell. So you get your tree built up. And if you've ever worked with Lisp much, you can easily make a malformed list. And that's using the dotted notation. And so it actually, like that. 1, 2, like that. But if you have two dots.
That dot there really just looks like an infixed version of cons, though.
Yes, that is the conventional way of depicting a cons.
Okay.
But this is what's going on under the surface. We need one more there. This is what's going on with Lisp and scheme lists.
Okay.
So they're effectively, linked lists using this, and I think this how will this do? 1. I think it will do it like that, or something like that. Anyway, it'll render it partially as a list, but not completely.
Okay.
Because it doesn't actually have the nil to make it properly formed. So we could use these cons and cars to build up this exact same data structure. Because this is going to be, that's going to result from cons. What this shows us, this can easily be the representation we had going on behind the scenes. It doesn't matter from that perspective.
Mm-hmm. This seems kind of like the church numerals, where I assume like real implementations don't actually do it this way for efficiency, but
yes.
It's conceptual.
Yeah, absolutely. Yeah, I mean, I think that really the value here is sort of the idea, the practice you get moving the lambdas around.
Right.
So like the church numerals, there's too many lambdas and too many parentheses for it to be clean. So I think it kind of disguises the insights a little bit. So you just sort of do the substitutions, and if you get it right, everything sorts out. But to get this one, it's simple enough that you can sort of slot the lambdas into the places, because you're really only working with 2 lambdas here. But they interact with each other in an interesting way. You got the first lambda that was returned by the cons, then the second lambda, which is passed to the lambda that was returned by the cons. So at the in-person session in King of Prussia, these were the main exercises that we discussed. I don't know that we spent a lot of time on any of the other ones. I don't know, any thoughts? Anything you guys want to discuss here?
I think that was very helpful. This really appreciate the going through this with us. I feel pretty good after that, though.
Okay, awesome. Yeah, I mean, if I'm not sure this will. If you have some time, there's no harm with spending, some time with the exercises in 2.4. But yeah. They're sort of more practice thinking through how you write code. But I think the difficulty here is that you're not an undergrad at MIT. So So the examples that this book picks are not necessarily the best examples for like a working computer science professional.
Mm.
And so I'm not sure that there's a huge amount of insight to be gained there. I mean, I'd work through, if you feel like it, maybe just do a few of them. I don't think you need to feel, like once you get up to like 213, where you're showing there's a formula for how, the tolerances are added up and so on. I mean, it's useful stuff, but I don't think it's sort of right at the core insight that the book is trying to lead you to. And of course, there's exercise 216, which includes the warning, this problem is very difficult.
216.
And yeah. So I'm not sure you'd want to sink, too much of your life into solving that one. There is one later in the book where the authors mention that a good solution to this problem is probably worth a PhD.
Wow.
Did anybody solve that?
That's later in the book. We'll see. I'll have to search online for solutions to that one. I suspect I won't be making it all the way through that one myself. But so sort of, I think that sections, or Chapter 1 and Chapter 2 are really still laying the groundwork. Once we get to section 2.4, that's when I think we're really starting to get into some of the more interesting stuff. Section 2.2 has a lot of exercises in it, and the King of Prussia group said that they were thinking they might want to split them into 2 sections so as to not overwhelm people. And so let me just check the last discussion to see if Steve posted what the plan was for the next meeting.
I need to grab my power cord, actually.
Oh yeah, sure. Okay, passkeys. Let's see here. Okay, yeah, Steve didn't say. Let me take a quick look here. Okay, well, section 2.2 is huge. Let's see. I'm just flipping back over to. There, just can't find my screen share there. Okay, so I was just having a look here. Yeah, so as I was saying, section 2.2 is huge, and it also includes the picture language stuff. Vic, which scheme implementation are you using?
I've been bouncing around. I have Racket installed, and then I've been doing some of the stuff in Clojure, too.
Gotcha. How about you, Michael?
Racket.
Racket. Okay. So have you both found the SICP extensions for Racket?
I have not.
Okay. They're posted. I've sent them to the discussion list for Clojadelphia. I'll try to send them out again since we're getting close to that point. It's not for this next this next meeting, but the following one probably. That it will be really important because that's the one that has the picture language stuff. So section 2.2.4 uses a little DSL for manipulating pictures and graphically. And somebody has, so that was you need a bunch of lower level things to support that, and those are provided by this package by Neil Van Dyke, I think his name is. And it's pretty straightforward. You just have to stick a particular directive at the start of your file. Let's see here, and I think it is lang. And is anybody working using org mode Babel, or are you just working within by calling it directly?
Yeah,
Okay.
just REPL.
Or
I'm just using Racket REPL or
Dr. Racket?
yeah.
Okay, that's a good choice. That makes things a lot easier.
Or
So I just beg your pardon. Try again.
No, go ahead.
Okay, so I just typed in chat there. If you put that string at the start of your Racket file, that engages the SICP compatibility mode that somebody has written. So it's a slightly different dialect of scheme. And it also pulls in the picture language stuff. So there's a few exercises. There were a couple of things like measuring time and so on. There are a little different between the version of MIT scheme that was used by the authors and then sort of the modern Racket versions of those utilities. So, so you'll probably want to do that when you get to 224 for certain.
Yeah, that appears to be about 44 pages in the hardcover.
224? Yeah,
Well,
it's
well, I mean, 2.2 in general.
Oh, yes. And so there were like, I forget how many exercises in this first one. There's about twice that for this next one. So I'm just trying to figure out.
53.
Ha, okay.
52.
Okay. Yeah, so I think for the next one, it's just going to be sections 221 and 222.
Oh, gotcha.
But I'll confirm that with Steve to see what's going on in the KOP group, so we sort of stay synced up here. Because we're now getting to the point. I mean, the first couple of sections were pretty easy to breeze through a lot of the exercises. Some of them were heavy, but it wasn't too deep. And a couple of these, I think, will take more work. So there shouldn't be a huge amount of reading for the next section, though. It's pretty straightforward. And so the next section is going to be basically about building up lists. And anything else? No, basically using con cells to build lists and trees. So pretty straightforward stuff. And then using these as interfaces to pass through functions. So again, nothing that's too the waters aren't getting too deep compared to stuff you've seen in Clojure or other functional languages.
Yeah.
Any other thoughts or anything else anybody wants to discuss here?
Thanks for the notes. I mean, they'll be helpful for going back over this.
Okay, yeah. At the start, I posted, that's a link to the HTML rendering in my GitHub, so all of my solutions to these exercises are up there. I don't, as I said, have exercises to everything. I've got commentary on some of them, but not on all. So that's you can certainly take a look at those if you want, sort of to see how I've been tackling some of them. I haven't tackled any of the 2.2 ones yet, so my time has been starting to get taken up with other things, but I'll try to keep up.
Okay.
Guess that's it for tonight.
I guess so. Okay, well, thanks a lot, guys. Sorry that it's a little awkward starting out with all of the technical issues here. At least, I need to make a note how to get that invite URL out of Google Hangout. So hopefully that will be a little smoother starting up next time.
Yeah.
Okay.
Thank you very much, Paul.
Thank you.
Oh yeah, well thanks a lot, guys. It's good that we're have some people who are continuing here. I think it's going to be harder and harder to keep people coming to these as we get deeper into the book. But
Yeah, it starts to be a lot of time.
yeah, absolutely. So, but again, as we've been saying at both of these, we shouldn't if we can't make it through it, it's more important. If you don't hit everything in one pass through, whatever you hit will help the next time you tackle the book. So.
Right.
Just keep coming to the discussions, even if you haven't had a chance to read, or if you've only had a chance to read and haven't really tackled the problems. Just whatever you can manage to do to keep moving along.
Yeah. Great. Well, thank you very much.
Oh, awesome. Yeah, thanks a lot, guys. And I'll see you at a future meeting here.
Okay.
Good night.
Okay.
Bye.
Good night.